On a dark autumn night, if the air is clean and the city has not erased the sky, there is a soft stain of light in Andromeda that looks almost harmless. It is not bright enough to command attention. It does not flash. It does not move. It waits above the trees like a breath on glass, a pale cloud so faint that the eye can lose it simply by looking too directly. And yet that small blur is a trap for the human mind. It is the nearest major galaxy to our own, and that phrase makes it sound like a neighbor. But the light in that blur began its journey before the human species existed. It crossed intergalactic space while ice ages came and went, while animals rose and vanished, while our ancestors learned to chip stone, speak, build fires, bury the dead, make cities, write names, launch rockets, and finally build telescopes capable of understanding what the blur actually is. And only now has that light arrived. The comfortable belief is that a visible galaxy is at least somehow within the geography of our future. Maybe not tomorrow, maybe not this civilization, maybe not any technology we can build now, but somewhere in the imagination, Andromeda becomes a destination. We call it the galaxy next door. We say the Milky Way and Andromeda are neighbors. We show them in simulations as two spirals drifting toward each other, and the language quietly softens the distance. A neighbor is something you can reach. A next-door object belongs to the same scale as you. The argument of this journey is more uncomfortable. Andromeda may be the nearest large galaxy, but it is not near in any human sense. It is the first honest boundary between the universe we can study and the universe we can touch. Its light gives us knowledge, but its distance denies access. That is the tension the galaxy forces on us. The nearest major galaxy is not proof that the cosmos is open to us. It may be the clearest proof that most of the cosmos is forever an observed world, not an inhabited one. A fair objection has to be stated at the beginning, because without it, the argument becomes too easy. Human beings have repeatedly confused impossible with merely difficult. The ocean was once a boundary. Mountains were once barriers. The moon was once a symbol of the unreachable, and then 12 human beings left footprints there. It would be careless to say that no future intelligence could ever do what we cannot imagine. Relativity itself allows strange outcomes. At speeds extremely close to light speed, time aboard a spacecraft would slow relative to Earth. A traveler could, in principle, experience a much shorter voyage than the millions of years that pass outside. Speculative geometries, such as wormholes or warp drives, appear in equations under special assumptions. The future may contain engineering that would look like magic to us. That objection matters. But it does not dissolve the distance. It simply moves the burden of proof. The known universe does not owe us a shortcut, and every known way of crossing intergalactic space requires either impossible energy, impossible duration, or a one-way exile from every world the traveler ever knew. So begin with the blur itself. The Andromeda Galaxy, also called Messier 31, is visible to the unaided eye from a dark northern sky. It lies in the constellation Andromeda, near the familiar W of Cassiopeia, and not far from the Great Square of Pegasus. To a casual observer, it resembles a detached piece of mist. Through binoculars, it becomes larger and more elongated. Through a telescope, its bright central region burns like a small, ghostly lamp, while its full disk remains too wide and too faint for a narrow eyepiece to hold. If human eyes were more sensitive to low surface brightness, Andromeda would not look small at all. Its full apparent size would stretch several times wider than the full moon. The reason it looks modest is not because it is small, but because its light is spread thinly across the sky after traveling a distance that no human intuition can contain. For most of recorded history, no one knew what that cloudy object was. In the 10th century, the Persian astronomer Abd al-Rahman al-Sufi described it as a little cloud in his Book of Fixed Stars. That description was not wrong. It was honest. To the naked eye, it is a little cloud. Later astronomers catalogued it among nebulae, among fuzzy objects that were not stars and not planets and not comets. Charles Messier placed it in his catalogue as M31, not because he understood its grandeur, but because he wanted comet hunters to avoid mistaking it for a comet. It was a nuisance object, a permanent smudge in the sky that did not behave like the transient bodies he was hunting. There is something almost comic in that history. One of the most important objects in cosmology first survived in catalogues because it was not what people were looking for. The deeper error was not Messier's. It belonged to the whole scientific imagination of the time. For centuries, many astronomers assumed that the Milky Way was the universe. All stars, all clouds, all mysterious spirals lay inside one immense stellar system. When telescopes improved and spiral nebulae appeared, they were often treated as nearby structures, perhaps star-forming clouds or rotating systems inside the Milky Way itself. It was not foolish. The data were incomplete. Distances in astronomy are never obvious. A dim object can be small and nearby, or enormous and distant. Without a reliable distance method, the eye cannot decide. Andromeda could be a cloud inside our galaxy, or a galaxy of its own. The difference between those answers was not a detail. It was the difference between a universe with one galaxy and a universe with countless galaxies. That question became public in the famous debate of 1920. Harlow Shapley argued for a large Milky Way with the spiral nebulae inside it. He had strong reasons for thinking the Milky Way was much larger than older estimates, though some of his conclusions went too far. Haber Curtis argued that the spiral nebulae were separate island universes. He had clues. Novae in Andromeda appeared faint. Dark lanes in spiral nebulae resembled dust features seen in galaxies, and the whole structure seemed too organized to be a mere gas cloud. But he did not yet have decisive proof. The debate did not settle the matter. It preserved a moment when the size of the universe still hung between two incompatible possibilities. Either everything was inside one vast galaxy, or our galaxy was only one island among many. The proof came through the kind of star that quietly changed the scale of existence. Cepheid variables pulse in a regular way. Their period is linked to their true luminosity, a relation discovered by Henrietta Swan Leavitt while studying variable stars in the Magellanic Clouds. If you know the period, you can know how bright the star truly is. If you compare that true brightness with how faint it appears from Earth, the distance follows. Edwin Hubble used the 100-inch Hooker telescope at Mount Wilson to identify Cepheid variables in Andromeda. When he measured them, the result was devastating to the old picture. Andromeda was far beyond the Milky Way. It was not a nebula inside our home galaxy. It was another galaxy entirely. That discovery did not simply add a new object to the map. It destroyed the map and forced astronomy to draw a larger one. The Milky Way was no longer the universe. It was a galaxy. The word galaxy itself changed meaning. What had seemed like everything became one member of a larger population. Andromeda became the first undeniable proof that the cosmos contained other stellar systems comparable to our own. From that moment onward, the universe was not a single island of stars surrounded by darkness. It was an ocean full of islands, and the nearest large island had been visible to us all along as a smudge in the autumn sky. That is why Andromeda matters beyond its beauty. It was the object that taught humanity the difference between a galaxy and the universe. Today, we know far more about Andromeda than Hubble could have imagined. It is a large spiral galaxy, broadly similar to the Milky Way, but not identical. It contains a bright central bulge, a disk filled with dust lanes and star-forming regions, a halo of older stars and globular clusters, and a supermassive black hole at its center. Estimates vary, but Andromeda may contain roughly 1 trillion stars, many more than the usual estimates for the Milky Way's stellar population. Its disk stretches on the order of hundreds of thousands of light-years across, and its faint outskirts extend even farther into a halo that blends into intergalactic space. It is not merely a bright object. It is an entire civilization-sized stage repeated beyond counting. A galaxy with star clusters, stellar streams, satellite galaxies, planetary systems, dead stars, newborn stars, dust, gas, and the gravitational memory of older collisions. In January 2025, the Hubble Space Telescope's Great Andromeda Mosaic sharpened this intimacy in a way almost impossible to overstate. After more than a decade of observations and hundreds of separate pointings, astronomers assembled a panoramic view containing about 2.5 billion pixels and the glow of roughly 200 million resolved stars. That number is astonishing, and it is still only a fraction of Andromeda's true stellar population. Hubble can pick out the brighter stars across a portion of the galaxy, but countless red dwarfs and dim stellar remnants remain below the threshold of easy detection. The mosaic is both complete and incomplete at once. The most detailed portrait of another spiral galaxy ever assembled, and still only a shallow sampling of what that galaxy contains. It lets us see the texture of another island universe, but it also reminds us that even our best images are a partial translation of a reality too vast to hold. This is where the paradox begins to sharpen. Andromeda is close enough for us to resolve millions of individual stars. It is close enough to study its star clusters, dust lanes, stellar streams, and merger history. It is close enough that its light can be gathered by backyard cameras and by the most sophisticated telescopes humanity has built. Yet it is 2.5 million light-years away. These two truths do not fit comfortably together. The mind wants visibility to imply nearness. It wants a thing that can be photographed to be somehow less remote than a thing that cannot. Andromeda punishes that intuition. It is visible not because it is close in a human sense, but because it is enormous. 1 trillion stars can make themselves seen across a void that light needs millions of years to cross. A light-year is already an aggressive unit. It sounds gentle because the word year feels familiar, but the distance inside it is nearly 6 trillion miles, or about 9.46 trillion kilometers. Light travels at about 299,792 kilometers per second in vacuum. In 1 second, it crosses the distance that would take a jet aircraft many hours. In a little over a second, it reaches the moon. In about 8 minutes and 20 seconds, It comes from the Sun to Earth. In 1 year, it crosses a distance that no spacecraft has ever approached. And Andromeda is not 1 light-year away. It is not 10. It is not 1,000. It is 2.5 million light-years away. Say the number 2 quickly, and it becomes harmless. Slow it down, and it becomes an accusation against the imagination. The light entering your eye from Andromeda has been traveling for about 2.5 million years. When it left, there were no cities on Earth. There was no language in the modern sense, no agriculture, no art that we can recognize as ours, no species called Homo sapiens. Early members of the human lineage were beginning to shape stone and survive in changing landscapes. The Pleistocene was beginning. Ice sheets would advance and retreat many times before the photons reached the final part of their journey. Mammoths, mastodons, saber-toothed cats, giant ground sloths, and countless other creatures would live and vanish during the crossing. Continents would shift, climates would swing, coastlines would move, and the whole story of humanity would unfold during the time required for one beam of light to travel from the nearest major galaxy to Earth. This is why the word neighbor can mislead. It is not wrong. Andromeda is our nearest large galactic neighbor. It belongs to the local group, the gravitational family of galaxies that includes the Milky Way, Andromeda, Triangulum, and many dwarf systems. Compared with the great distances to galaxy clusters beyond our local environment, Andromeda really is nearby. The Virgo cluster is tens of millions of light-years away. More distant clusters lie hundreds of millions or billions of light-years away. On the scale of the cosmic web, Andromeda is close. But human language was not built for the cosmic web. When we hear neighbor, we imagine access. Astronomy means relation. Those are not the same thing. To feel the difference, start with the distances humanity has actually touched. The Moon is about 384,000 kilometers away on average. The Apollo spacecraft crossed that gap in roughly 3 days. The Moon is far enough that the radio delay becomes noticeable, far enough that Earth shrinks into a blue sphere, far enough that the journey required the largest rockets ever built at the time. Yet in cosmic terms, the Moon is not distant at all. It is part of the immediate Earth system. Light crosses the gap in about 1.3 seconds. You can look at the Moon and see it almost as it is now. The lunar distance is large enough to humble engineering, but not large enough to challenge the basic continuity of human action. The Sun is much farther. It lies about 150 million kilometers from Earth, or about 93 million miles. Light from the Sun takes about 8 minutes to reach us. If the Sun vanished in some impossible instant, Earth would continue orbiting the empty point for 8 minutes, because gravity itself, in general relativity, communicates changes at the speed of light. The Parker Solar Probe has flown closer to the Sun than any previous spacecraft, and reached record speeds during its solar passes, hundreds of thousands of miles per hour. These numbers feel extreme, and they are extreme. Yet they remain solar system numbers, distances within the gravitational household of one star. They are the measurements of a home, not of the space between homes. The outer solar system stretches the mind further. Mars can be tens or hundreds of millions of kilometers away, depending on orbital positions. Jupiter lies many hundreds of millions of kilometers from the Sun. Saturn, Uranus, and Neptune stretch the scale outward until sunlight itself needs hours to reach the farthest major planets. Voyager 2 took 12 years to reach Neptune after its 1977 launch, helped by gravitational assists from the giant planets. Voyager 1, now far beyond the planets, is the most distant operating human-made object. It has crossed the heliopause, the region where the solar wind gives way to interstellar space. After nearly half a century, it has traveled tens of billions of kilometers. That is magnificent. It is also almost nothing compared with the distances to the stars. The nearest star system, Alpha Centauri, lies a little more than 4 light-years away. Proxima Centauri, the faint red dwarf member of that system, is currently the closest individual star to the Sun. 4 light-years is the smallest serious interstellar distance available to us, the nearest step outside our stellar home. Light itself takes more than 4 years to cross it. Voyager 1, at its present speed, would require tens of thousands of years to cover that distance if it were aimed correctly, which it is not. Even the Parker Solar Probe's record speeds would shrink the time dramatically, but still leave a journey measured in thousands of years. The first star beyond the Sun is already outside the time scale of any normal civilization. That is only the first rung. The Milky Way is about 100,000 light-years across in its bright stellar disk, with fainter halo structures extending farther. Our Sun sits roughly 26,000 light-years from the galactic center. It takes light about 100,000 years to cross the visible disk from one side to the other. A radio message from one edge of the galaxy to the other, if somehow aimed and received, would require 100 millennia to arrive. A reply would take another 100 millennia. That is a conversation longer than the existence of our species in its modern form. The Milky Way contains hundreds of billions of stars, but those stars are separated by enormous gaps. It is a city of suns where each house is several light-years from the next, and the city itself is too wide for light to cross in the span of human history. Now compare Andromeda. It is about 25 times farther away than the entire width of the Milky Way's disk. If the Milky Way were reduced to a dinner plate, Andromeda would not be touching it. It would sit several meters away across a room of dark air. If the Milky Way were a football field from one galactic edge to the other, Andromeda would be about 25 football fields away. That is the gap between the two nearest major galaxies. The space between them is not crowded with stars. It is mostly intergalactic medium, extremely thin gas, dark matter, and scattered dwarf galaxies. On the scale of ordinary matter, it is emptiness almost beyond comparison. The interstellar medium inside a galaxy may contain roughly 1 atom per cubic centimeter in some regions, sometimes more in clouds, and far less in hot bubbles. The intergalactic medium between galaxies can be far thinner, often described in terms of atoms per cubic meter rather than per cubic centimeter. Human-made vacuums in laboratories are dense compared with these cosmic spaces. A spacecraft crossing the void between the Milky Way and Andromeda would not move past frequent landmarks. It would not pass star after star, as if sailing among islands. It would move through a desert without sand, an ocean without water, a geography made mostly of absence. Behind it, the Milky Way would slowly shrink into a spiral glow. Ahead, Andromeda would slowly widen. Between those changes would be a duration so long that the word voyage begins to fail. This is the first major pressure point in the argument. Inside a galaxy, impossible distances are still connected by membership in the same structure. Stars orbit a common galactic center. Gas flows along spiral arms. Stellar streams trace ancient mergers. There is at least a kind of shared environment. Between galaxies, even that weak comfort disappears. Intergalactic space belongs to no star. It is the space between islands, and the islands themselves are separated not by rivers, but by oceans of near nothing. Andromeda is not merely farther than Alpha Centauri. It is remote in a different category. Interstellar distance and intergalactic distance are both measured in light years, but measuring both with the same unit can hide how different they are. Now translate the distance into travel time. This is where optimism begins to negotiate with arithmetic, and arithmetic does not negotiate back. A light signal takes 2.5 million years to reach Andromeda. That is the absolute minimum for any information traveling according to known physics. A physical object with mass cannot reach light speed. At our fastest achieved spacecraft speeds, a trip to Andromeda would take billions of years. At 1% of light speed, which is already far beyond present spacecraft capability for a durable mission, the journey takes about 250 million years. At 10% of light speed, a velocity that introduces enormous energy and collision hazards, it still takes about 25 million years. Even at half the speed of light, the external time is 5 million years. The distance is not merely long. It is biologically, geologically, and civilizationally long. A probe traveling for 250 million years is not on a mission in any normal sense. It is participating in geology. It leaves during one planetary epoch and arrives during another. The continents may have rearranged. Ice ages may have come and gone. Species may have evolved into successors or disappeared entirely. The civilization that launched it would almost certainly not exist in a recognizable form. Its languages would be gone, its institutions gone, its memory broken or transformed beyond continuity. The probe might arrive as an artifact with no living community left to receive its report. It would be less like exploration and more like throwing a message into a future ocean whose shore you cannot imagine. The strongest counterargument returns here. Relativistic travel changes the personal experience of time. If a spacecraft could accelerate to a velocity extremely close to light speed, the travelers inside might experience far less than 2.5 million years. In principle, a sufficiently advanced ship under continuous acceleration and deceleration could allow occupants to reach a distant galaxy within a human lifetime of ship time. This is not fantasy in the sense of violating relativity. It is a real consequence of special relativity. Time dilation is measured and confirmed. Fast-moving clocks tick differently from stationary ones. The objection is serious because it shows that light years do not always translate directly into traveler aging. But the price is brutal. First, the outside universe still ages by millions of years. A traveler who reached Andromeda in one lifetime of ship time would not have connected the two civilizations in any ordinary way. They would have left Earth and arrived after Earth had experienced geological time. Second, the energy required to accelerate a large spacecraft to such speeds is far beyond anything humanity controls. As velocity approaches the speed of light, kinetic energy grows without bound. A ship at relativistic speed also faces the problem of collisions with dust and gas. A tiny grain becomes a high-energy projectile. Shielding, navigation, propulsion, deceleration, radiation, life support, and communication all become problems on scales that no present engineering can solve. Relativity does not make Andromeda reachable. It makes it possible to imagine a one-way exile into another epoch. This distinction matters because popular imagination often treats time dilation as a loophole. It is not a loophole for civilization. It is, at best, a loophole for an individual traveler or a small crew, and even that requires energy and engineering beyond our horizon. The traveler may arrive alive, but everything behind them has fallen into the deep past. Their home world has aged by millions of years. The message they carry belongs to a dead moment. The arrival would not be a triumphant bridge between galaxies. It would be a form of cosmic orphaning. If a traveler left Earth for Andromeda and survived the crossing through relativistic time dilation, they would step into another galaxy as the last living witness of an Earth that no longer exists in the form they remember. Communication is less dramatic but more unforgiving. A radio signal to Andromeda takes 2.5 million years to arrive. A reply takes another 2.5 million years to return. A single exchange spans 5 million years. That is not a conversation. It is a pair of fossils made of information. The senders and receivers cannot share a political era, a language era, a biological era, or perhaps even a species identity. Imagine sending a greeting to Andromeda from Earth 5 million years ago. The beings who sent it would not have been human. If a reply arrived now, there would be no continuity of memory between sender and receiver. The signal could be decoded, perhaps, but the relationship would be severed by time. Intergalactic communication does not fail because radio waves are slow. It fails because light speed, the fastest communication speed possible, is still slow compared with the space between galaxies. And yet we do communicate with Andromeda in one direction. The galaxy sends us its past continuously. Every telescope pointed at it receives photons that left millions of years ago. We can read those photons. We can reconstruct stellar populations, estimate metallicities, trace dust lanes, study globular clusters, examine streams from swallowed satellite galaxies, and infer the mass distribution that includes dark matter. This is one of astronomy's great asymmetries. The universe can be known without being reached. Photons are messengers that do not need permission. They arrive with ancient news, and we build instruments to interpret them. Knowledge flows across the void, even when bodies cannot. That asymmetry is not a consolation without cost. It changes what kind of creatures we are in the cosmos. We are not explorers of the universe in the physical sense that science fiction prefers. We are readers of ancient light. We are archaeologists of photons. We study objects that are already separated from us by time as well as distance. Andromeda, as we see it, is not Andromeda now. It is Andromeda 2.5 million years ago. The Andromeda that exists at this moment. In whatever sense simultaneity can be defined across such distances, is unknowable to us until its present light arrives in the far future. We are neighbors only by gravitational relation. Observationally, we live in different ages. The history of Andromeda itself deepens that sense of estrangement. It has not been a calm spiral through all time. Hubble's detailed surveys and ground-based spectroscopy suggest a galaxy marked by mergers, streams, and episodes of star formation shaped by accretion. It has absorbed smaller systems. Its halo contains stellar debris from past interactions. Its disk bears the memory of disturbance. In January 2025, The Great Hubble Photomosaic did more than produce a beautiful picture. It allowed astronomers to compare populations across Andromeda's northern and southern disk, to read differences in age and chemical enrichment, and to infer a more active merger history than the Milky Way's recent past. The galaxy next door is not a static picture. It is a living gravitational record of violence, growth, and change. There is a temptation to make Andromeda into a mirror of the Milky Way because comparison is useful and emotionally satisfying. The two galaxies are both large spirals in the local group. They are the dominant masses in our neighborhood. They may have broadly similar structures: disks, bulges, halos, globular clusters, dark matter halos, satellite systems. But a mirror is not the same as a twin. Andromeda appears to have more stars. Its central black hole is far more massive than Sagittarius A star, the black hole at the center of the Milky Way. Its merger history may have been more active in the recent cosmic past. Its disk and halo preserve different scars. To study Andromeda is not simply to see our own galaxy from outside. It is to see a related but independent answer to the question of what a large spiral galaxy can become. That is scientifically invaluable because we cannot step outside the Milky Way to photograph our own galaxy as a whole. We live inside the disk, surrounded by dust and stars. Mapping our galaxy from within is like reconstructing a city while standing in one street and peering through fog. Andromeda gives us an external comparison. It lets us test models of spiral structure, satellite accretion, stellar halo formation, star formation history, and dark matter distribution. It is close enough for individual stars to be resolved in extraordinary numbers, but far enough that its whole structure fits into a coherent external view. In that sense, Andromeda is both neighbor and laboratory. The controversy is not whether Andromeda matters. It plainly does. The controversy is what its nearness should mean. One view says Andromeda invites expansion of imagination. If we can see a trillion-star galaxy with the naked eye, perhaps one day intelligence will reach it. Another view says the opposite. Andromeda is precisely where imagination must stop pretending scale is negotiable. The galaxy is near enough to teach us and too far to receive us. It is a boundary object. It sits at the edge of what human curiosity can convert into knowledge, and beyond what human engineering can convert into presence. That boundary is not a failure of courage. It is a property of space-time. The coming merger between the Milky Way and Andromeda complicates the story in a fascinating way. For decades, popular accounts often stated with confidence that the two galaxies would collide in about 4 to 5 billion years. The radial velocity of Andromeda shows that it is moving toward us at about 110 kilometers per second. Earlier, Hubble measurements of its sideways motion suggested a future encounter. In this classical picture, the two spirals would pass through each other, distort into tidal tails, interact again, and eventually settle into a larger elliptical-like remnant, sometimes nicknamed Milkomeda. The night sky of the far future would be transformed as Andromeda swelled from a faint smudge into a vast structure of stars. More recent work has made the outcome less simple. A 2025 Nature astronomy study using updated data and simulations argued that the merger is not guaranteed within the next 10 billion years, with the gravitational influence of the Large Magellanic Cloud and Triangulum altering the odds. A 2026 analysis using updated Gaia-based proper motions argued that the probability may again be high, around 90% in its fiducial model, while still emphasizing that current uncertainties matter. This is a wonderful example of science becoming more interesting when it becomes less absolute. The old story, one inevitable collision in about 5 billion years, was clean. The newer story is messier, a likely or possible future interaction whose timing and certainty depend sensitively on tiny motions measured across millions of light-years. This uncertainty does not weaken the main point. It strengthens it. Two enormous galaxies, gravitationally bound, approaching at more than 100 kilometers per second, may still require billions of years to merge, and the detailed outcome remains sensitive to small uncertainties in motion and mass. That is what distance does. It turns a dramatic velocity into a slow drift. It makes gravity patient. And it reveals how misleading speed can sound when separated from scale. 100 kilometers per second is fast enough to cross continents in minutes. It is not fast enough to make Andromeda feel near. Even the universe itself, pulling two galaxies together through gravity, works on timescales that swallow the history of life. If the galaxies do merge, the event will not resemble a collision of solid objects. Stars are tiny compared with the spaces between them. When two galaxies pass through one another, their stars almost never physically collide. The structures distort because of gravity. Gas clouds compress and may trigger star formation. Orbits are rearranged. Streams and shells form. Central black holes may eventually spiral together, but the stars themselves mostly pass through the expanded gravitational dance without direct impact. If the Sun is still present when the encounter occurs, it may be thrown into a different orbit in the merged remnant. Earth, if it still exists in any habitable form, will have far more immediate problems from the evolving Sun, long before Andromeda's stars become a direct concern. This future encounter can tempt us into saying that Andromeda is not really unreachable, because it will come to us. But that misses the nature of reach. If a mountain slides across a continent over geological time and eventually arrives where you stand, that is not the same as climbing the mountain. The galaxies may merge because gravity has billions of years to spend. That does not make intergalactic travel a project for living beings. It only shows that the universe can do with deep time what organisms cannot do with intention. Gravity has no lifespan. It does not grow impatient. It does not need a mission plan. It simply curves trajectories, moment after moment, until structures that seemed separate become entangled. The future merger, uncertain in timing and probability but possible and perhaps likely, creates a haunting reversal. Andromeda may be impossible for us to visit, yet it may not remain separate forever. The barrier that defeats travel may be erased by time. But if that happens, it will not be a triumph of civilization. It will be a consequence of dynamics, and it will happen in a future so distant that the human story as we know it may not be present to witness it. The nearest major galaxy is both permanently out of reach on human timescales and slowly approaching on cosmic timescales. The contradiction is not a mistake. It is how the universe holds scale. Now expand beyond Andromeda. The local group contains many smaller galaxies: Triangulum, the Magellanic Clouds, dwarf spheroidals, ultra-faint dwarfs, satellite systems around both the Milky Way and Andromeda. These galaxies matter, but they do not soften the loneliness. Most are small and faint. They are separated by enormous distances. They are not stepping stones in the way islands might be for sailors. A dwarf galaxy hundreds of thousands of light-years away is still impossibly far by any current standard, and it does not provide a natural fuel station, a safe harbor, or a bridge. It is an astrophysical object, not an infrastructure. The local group is not a neighborhood full of streets. It is a loose gravitational family spread across roughly 10 million light-years. Beyond the local group lies a still larger pattern. The Virgo cluster, tens of millions of light-years away, contains more than 1,000 galaxies. The local group itself is part of the larger Laniakea supercluster region, a vast flow of galaxies and groups shaped by gravity on scales of hundreds of millions of light-years. The cosmic web stretches beyond that. Filaments of galaxies, clusters at their intersections, and voids between them. On the largest scales, the universe resembles a network of luminous foam. The galaxies are not scattered randomly. They trace dark matter's invisible architecture. But that structure is a map of relation, not a map of reachability. The web connects matter gravitationally and historically. It does not create roads. If Andromeda is 2.5 million light-years away, the Virgo cluster is over 20 times farther. More distant galaxy clusters are hundreds or thousands of times farther still. The observable universe is about 93 billion light-years in diameter, not because the universe is older than 93 billion years, but because space itself has expanded while light has traveled. Every increase in scale pushes us deeper into the difference between seeing and going. The farther we look, the farther into the past we look. A galaxy 10 billion light-years away is not merely remote. It is ancient in our view. It belongs observationally to an earlier cosmic epoch. We do not see its present. The telescope is a time machine, but it is not a ship. Dark energy makes the boundary even colder. The expansion of the universe is accelerating. Galaxies outside gravitationally bound groups are receding from us as space expands. Beyond a certain cosmic horizon, light emitted now will never reach us, no matter how long we wait. Distant galaxies we can see today may already be permanently unreachable, even by light signals sent now. Their ancient light is in our sky because it left long ago, when the universe was smaller and the expansion between us was different. This is one of the most difficult facts in cosmology to feel. The visible universe is larger than the reachable universe. Seeing something does not mean it lies inside our future. The cosmos contains light from places that no message from us can ever influence. Andromeda is different because it is gravitationally bound to us. It is not being carried away by cosmic expansion. It is approaching, or at least moving, within the local group's gravitational dynamics. That makes it our final large companion in a universe where everything beyond our local gravitational island will eventually fade from practical reach. In the far future, if the expansion continues as currently understood, distant galaxies will disappear beyond the horizon, their light stretched and dimmed until they become undetectable. Future astronomers living in the merged remnant of the Milky Way and Andromeda might see a universe that appears far emptier than ours. They may lack access to the evidence that allowed us to infer cosmic expansion and the Big Bang. The sky itself is historically temporary. We live at a time when the wider universe is still visible. This gives Andromeda a strange emotional role. It is the nearest major galaxy, perhaps our future merger partner, our local counterpart, our greatest external spiral laboratory. It is also a sign of approaching cosmic solitude. If the rest of the universe is eventually carried out of view, Andromeda is the one large galaxy that remains inside our gravitational story. Its distance is terrifying, but its boundness is almost intimate. It is both unreachable by us and unable to escape the shared destiny of the local group. The universe denies us a voyage and offers instead a slow collision that no living traveler commands. That is not less strange. It may be stranger. Return now to the naked eye view. A faint oval blur. A galaxy of roughly 1 trillion stars. A light travel time of 2.5 million years. The most distant object most people can see without optical aid. If the full disk were bright enough, it would dominate the sky, but it is diluted by distance. This visual fact contains a lesson about surface brightness. Large astronomical objects can be hard to see because their light is spread over a wide area. Andromeda is intrinsically immense and luminous, yet to the eye it is fragile. It is not hiding because it is small. It is hiding because the universe stretches its light thin. The body that detonated our old concept of the universe presents itself as a whisper. There is beauty in that whisper, but beauty is not comfort. The public story often treats cosmic scale as uplifting. We are small, therefore our worries are small. We are star stuff, therefore we belong. There is truth in that. But Andromeda adds a more severe truth. We belong to the universe without being able to traverse it. We can be made of cosmic matter and still be physically confined. We can understand galaxies and still never enter another one. The same universe that produces consciousness also separates conscious islands by distances that make mutual presence impossible. This is not despair. It is a harsher form of wonder. The strongest hopeful view says that knowledge itself is a kind of travel. When Hubble resolves Andromeda's stars, when spectroscopy measures motion and composition, when simulations model its future, humanity extends itself through understanding. We do not need to carry bodies to Andromeda to bring Andromeda into the human story. Light has already crossed the distance. Mathematics lets us interpret it. Images let us feel it. The galaxy becomes part of culture, memory, and science. In that sense, we have already reached Andromeda in the only way a species like ours may ever reach another galaxy. We have turned its photons into knowledge. That counterargument is humane and partly right. Observation is not a lesser miracle. It is extraordinary that organisms on one planet can know the structure of a galaxy millions of light years away. No animal before us, as far as we know, looked at that smudge and understood it as another island of stars. To name Andromeda correctly is already a triumph over our scale. To map it star by star is almost absurdly powerful. Yet knowledge as travel has a limit. It can satisfy curiosity, but it cannot create contact. It can tell us what Andromeda was. It cannot place a hand on a rock orbiting one of its stars. It cannot shorten the light time. It cannot make a conversation with an Andromedan civilization possible. It is a profound substitute, but a substitute still. The distinction between contact and knowledge matters especially when we imagine life elsewhere. A galaxy with 1 trillion stars may contain countless planets. Many of those planets may be old. Some may have had stable conditions. It is not reckless to wonder whether life has arisen somewhere in Andromeda. It would be reckless to claim that it has. We do not know. We cannot currently detect Earth-like biospheres in another galaxy. A radio civilization in Andromeda, if it existed now, would be separated from us by a 2.5 million year one-way delay. Its broadcasts reaching us today would have been transmitted before humans existed. Our replies would reach them in a future their civilization might never see. Even if life is common, galaxies may remain silent to one another because time, not absence, prevents conversation. This reframes the Fermi-like intuition people bring to the sky. We often ask why we have not heard from anyone. But the Andromeda distance suggests a sharper question. What would hearing even mean across intergalactic time? A message from another galaxy is not a phone call. It is a fossilized event. It tells us that intelligence existed there millions of years ago, not that it exists now. A reply would be an offering to a future that has no obligation to preserve the recipient. Intergalactic communication would be less like dialogue and more like archaeology conducted by photons. The silence of galaxies may not only be about whether minds exist, it may be about whether minds can share a present. The scale also alters the meaning of exploration within our own galaxy. Interstellar travel to nearby stars is already daunting, perhaps centuries or millennia away in practical terms. But it belongs to the same galaxy, the same gravitational island. If humanity ever becomes a long-lived spacefaring species, it may be able to send probes or even habitats to nearby stars. It may slowly expand through a small neighborhood. It may build knowledge and infrastructure over enormous time. But Andromeda stands outside that dream. It shows the edge beyond which expansion becomes almost mythological. The reachable future, if there is one, is not the whole cosmos. It is a tiny region inside one galaxy. That realization can feel diminishing, but it can also clarify priorities. We do not need other galaxies to have a cosmic future. The Milky Way alone contains hundreds of billions of stars. Even a modest region around the Sun contains more worlds than humanity could study in any imaginable near future. The galaxy is not small. It is so large that even a civilization lasting millions of years might know only a fragment of it firsthand. Andromeda's inaccessibility does not make the universe useless to curiosity. It prevents a childish version of cosmic ambition from pretending the entire observable universe is a map of future destinations. The mature version of ambition begins by admitting that most of the universe is not territory. It is testimony. Andromeda is testimony to more than distance. It is testimony to the layered nature of time. The light we see from its disk left different parts of the galaxy, at slightly different times depending on depth and geometry. Its far side and near side are not presented to us in the same exact temporal slice. On a galaxy scale, even the object itself is spread through light time. We simplify and say Andromeda is 2.5 million light-years away, but the galaxy has thickness and width. Its full structure spans hundreds of thousands of light-years. That means the image is not one perfect now. It is a composite of ancient times across a structure so large that internal light time becomes meaningful. A galaxy is not a photograph taken at one instant by the universe. It is a tapestry of delayed signals. The same is true for the Milky Way, though we rarely think of it that way. When we look at stars in our own galaxy, we see them at different ages. Sirius as it was 8 or 9 years ago. Deneb as it was, perhaps thousands of years ago, depending on the exact distance estimate. The galactic center as it was tens of thousands of years ago, though dust hides most visible light from that region. Astronomy is not a view across space alone. It is a view across a broken present. Each photon carries a local truth from its own emission time. The sky is not synchronized. The night above us is a mosaic of histories. Andromeda magnifies this into a single naked-eye object. Its glow looks simultaneous. It feels like one thing. It is actually a trillion-star system delivered to us from deep time. And because the human eye cannot resolve the stars, all those histories blur into one silver smear. The mind sees a cloud. The telescope sees structure. The physics sees time. Each level reveals a different failure of the senses. The unaided eye is not wrong, but it is radically incomplete. This is one reason astronomy changes the emotional texture of reality. It teaches that familiar appearances can be truthful and deceptive at the same time. The source of the deception is not only human limitation, it is also the way the universe permits information to travel. Light preserves a record, but erases immediacy. The longer the distance, the older the record. This makes deep space a library whose books arrive from the past and cannot be updated on demand. Andromeda's book takes 2.5 million years per page. We are reading a chapter written before our species existed. The next chapter is already traveling. The current chapter will not arrive until a future Earth that may not contain anything like us. This is the sorrow beneath the beauty of the galaxy next door. Still, sorrow is not the same as hopelessness. There is an honest grandeur in accepting the boundary. Andromeda's distance does not make our knowledge meaningless. It makes it more remarkable. A creature that cannot cross the gap has learned to measure it. A species confined to one planet has identified individual stars in another galaxy. Brains evolved for tracking animals, and weather have built a cosmic distance ladder using pulsating stars, red giant branches, eclipsing binaries, and surface brightness fluctuations. The result is not myth. It is a set of measurements, with uncertainty bars, cross-checked by independent methods. The mind cannot feel 2.5 million light-years, but science can know it. That difference between feeling and knowing runs through the whole story. You cannot feel a trillion stars. You cannot feel 100,000 light-years. You cannot feel 2.5 million years of light travel. Your instincts compress them all into one category: far. Science refuses that compression. It keeps the ratios alive. The moon is 1.3 light seconds away. The sun is 8 light minutes away. Alpha Centauri is 4 light-years away. The Milky Way is about 100,000 light-years across. Andromeda is 2.5 million light-years away. Each step changes the type of problem. The latter is not only a scale of distance, it is a scale of broken intuition. The distance also reveals how local our stories are. Every war, empire, philosophy, religion, language, and technology in human history has unfolded on one planet during the final tiny fraction of Andromeda's light time. The photon that enters your eye from that galaxy has outlived all of it. It was already most of the way here when the first cities were built. It was almost done when writing began. It was in the last breath of its journey when telescopes were invented. It arrived after we finally learned to call its source a galaxy. There is something almost unbearable in that timing. The universe waited millions of years to deliver a message, and the species capable of reading it appeared at the very end. Perhaps that timing is normal. Perhaps consciousness always arrives late to the photons that made it possible. The heavy elements in our bodies were forged by earlier generations of stars. The planets formed long after the first light. Life arose after billions of years of planetary cooling and chemistry. Intelligence is not the beginning of the universe's story. It is a late development that looks backward through signals that have already traveled most of cosmic history. When we look at Andromeda, we do not stand outside time, gazing calmly at an object. We stand inside a chain of delayed causes, made of ancient matter, receiving ancient light, asking questions that arrived far later than the processes they question. This could make us feel irrelevant, but irrelevance is not the only interpretation. A small observer can still make a true measurement. A brief life can still contain an accurate idea. The scale of the universe does not shrink the validity of understanding. It only strips away fantasies of centrality and control. We are not central. We are not powerful on galactic scales. We are not destined by mere ambition to walk into every light we can see. But we are capable of knowing that. We are capable of being corrected by the sky. Andromeda's gift is not comfort. Its gift is scale with the illusion removed. The popular phrase, "galaxy next door," should not be abandoned. It should be heard correctly. A next-door galaxy in cosmic language is an object whose light travel time is older than our genus. A neighbor in the local group is a trillion-star system separated from us by a void wider than 25 Milky Ways placed end to end. Nearness in astronomy is not nearness in life. When astronomers speak this way, they are not lying. They are using words under different pressure. The same word becomes elastic enough to cover a house across the street and a galaxy millions of light years away. The danger lies not in the word, but in forgetting how much it is stretched. A reasonable objection is that this argument may be too severe. If Andromeda is visible, if its light reaches us, if gravity binds it to us, if it may one day merge with the Milky Way, why call it out of reach? The answer is because reach has to mean more than eventual gravitational contact. Reach means an action taken by beings within the continuity of their own history. Reach means a mission that can return information to the civilization that launched it, or at least to its descendants in a meaningful chain of memory. Reach means a destination that belongs to a future rather than to deep time. By that definition, Andromeda is not reachable. Not with known physics, not with present engineering, and not within the lifetimes of civilizations as we understand them. This is not the same as declaring all future possibilities closed. Science should be careful with the word impossible. It has been embarrassed by that word before. The safer and stronger claim is narrower. Andromeda is beyond meaningful access for any technology grounded in known, tested physics and any continuity of human civilization we can honestly describe. Exotic loopholes remain speculative. Relativistic travel creates exile rather than connection. Gravitational merger belongs to the universe, not to us. That is enough. The claim does not need absolute impossibility to matter. It only needs to show that the common emotional reading of Andromeda as a destination is scientifically misleading. There is another complication. Andromeda itself will not look the same by the time any signal or traveler could arrive. Over millions of years, stars orbit, gas moves, star formation changes, supernovae explode, clusters drift, and the galaxy evolves. A probe launched now, traveling impossibly close to light speed, would arrive at a different Andromeda than the one we observe. A probe traveling at any realistic sublight speed would arrive at a profoundly different era. The target is not frozen. No galaxy waits as a fixed object. The destination changes during the journey, and the launch world changes even more. Intergalactic travel is not only far, it is aimed at a moving future. Even within our observations, Andromeda's future is a calculation, not a memory. Astronomers measure proper motions, radial velocities, masses, and gravitational influences, then run simulations forward. Small uncertainties become large after billions of years. The role of Triangulum and the Large Magellanic Cloud matters. The mass of the Milky Way and Andromeda matters. The transverse velocity matters. Whether the galaxies merge, when they merge, how many close passages occur before coalescence, and what final remnant forms all depend on measurements that are still being refined. This is not a weakness of astronomy. It is the honest consequence of predicting a many-body gravitational system across times longer than Earth's remaining habitability. What we can say is that Andromeda and the Milky Way are not strangers in the expanding universe. They belong to the same bound region. They are close enough for gravity to matter across billions of years. They are far enough that human travel fails across any meaningful interval. This double identity is precisely what makes Andromeda the perfect pressure object. A more distant galaxy would be obviously unreachable. A nearby star would be difficult but still imaginable as a future target. Andromeda sits between those emotional categories. It looks like a neighbor and behaves like a boundary. It invites the wrong intuition and then corrects it with arithmetic. Imagine, for a moment, standing halfway between the Milky Way and Andromeda. There is no planet there, no station, no natural platform, but imagine a body suspended in the intergalactic dark. The Milky Way would be a great soft glow in one direction. Andromeda would be another in the opposite direction. Each would span a portion of the sky, brighter than they appear from Earth, but still remote. Around you would be an emptiness so deep that ordinary ideas of location might fail. The nearest stars would not be stars at all in the local sense, but the diluted lights of galaxies. You would not be in a solar system, not in a stellar neighborhood, not in a disk or halo where stars are common. You would be in the space between islands, with the islands themselves as distant lights. That imagined viewpoint exposes a hidden assumption. We often think of space as a place filled with objects separated by distance. But at intergalactic scale, space is mostly the absence of objects, with galaxies occupying tiny volumes compared with the voids around them. Matter is concentrated into islands and filaments, while most of the volume is dark, thin, and cold. The universe is not packed with destinations. It is structured by emptiness. The beauty of galaxies comes partly from how alone they are. Their spiral arms and glowing cores stand out because the background is so close to nothing. Andromeda's distance is not an exception to cosmic design. It is an expression of that design. This is also why images can be deceptive. Photographs of galaxies are often framed tightly. A spiral fills the image, bright and detailed. The black around it becomes a backdrop, not a subject. But the black is the subject too. The true scale of a galaxy includes the surrounding void that isolates it. Crop the image, and the galaxy becomes an object. Restore the scale, and it becomes an island. Beauty must not be allowed to erase the emptiness. The Andromeda Galaxy is magnificent, but its magnificence is inseparable from the gulf that makes it untouchable. There is a quiet, ethical dimension to this. Sensational accounts often turn mystery into conquest. It implies that every boundary exists so that we can break it. But some boundaries may exist to teach proportion. Andromeda does not need to be visited to matter. It does not need to be conquered to be known. The mature response to the galaxy next door may not be a vow that one day we will go there. It may be the ability to stand beneath its ancient light and understand what kind of distance separates knowledge from possession. The universe is not less wondrous because we cannot own it with footprints. The story of Hubble's Cephids already taught one humility. Our galaxy was not the universe. Andromeda's distance teaches another. The universe is not a landscape arranged for our movement. The first lesson displaced us from cosmic centrality. The second displaces us from cosmic access. We are not at the center, and we are not free to cross the whole. What remains is not nothing. What remains is observation, understanding, and perhaps stewardship of the small, reachable region we do inhabit. There is dignity in that if we can accept it without shrinking it into despair or inflating it into fantasy. The scientific method itself is built for this kind of humility. It does not require that a thing be reachable. It requires that evidence be measurable. Andromeda's distance can be measured by Cepheids, red giant branch stars, eclipsing binaries, and other techniques. Its motion can be measured by spectroscopy and astrometry. Its stellar populations can be studied through photometry. Its dark matter halo can be inferred from motions and gravitational effects. Its future can be modeled probabilistically. None of this requires physical access. Science is a way of making contact with the unreachable through evidence, but it must also mark where evidence ends. A good model is not a spaceship. A beautiful image is not proximity. A measured distance is not a road. In that sense, Andromeda is not a failure of exploration. It is one of exploration's purest forms. We receive photons that no one sent deliberately. We translate them into structure, history, and dynamics. We learn that the galaxy has star-forming rings, dust lanes, globular clusters, satellites, streams, and a central black hole. We learn that its stellar populations are not uniform. We learn that it carries evidence of past mergers. We learn that its motion toward us is real, while its future path remains subject to uncertainty. And then we place all of that knowledge beside the travel time and admit that knowing is not going. The admission is not defeat. It is accuracy. There is one more optimistic proposal that deserves a fair hearing. The generation ship. If a vessel could be made large enough, self-sustaining enough, and culturally stable enough, perhaps it would not matter that a journey lasts millions of years. The people who arrive would not be the people who departed, but that is already true of every long civilization. We inherit projects we did not begin. Cathedrals took generations. Languages and institutions outlive their founders. A generation ship scales that logic into space. It imagines a mobile world, carrying ecosystems, memory, children, education, repair systems, archives, and a destination so remote that no original traveler could ever expect to see it. In principle, this does not violate physics. A slow ship can cross any finite distance if it survives long enough. But here again, the word finite hides the real problem. A generation ship to a nearby star is already one of the hardest ideas ever seriously imagined. It must preserve life, governance, technology, genetic diversity, motivation, and purpose across centuries or millennia. A generation ship to Andromeda would have to preserve them across millions of years. That is not just a larger version of the same challenge. It changes the category. Languages change beyond recognition in 1,000 years. Species evolve over millions. Geological records are erased and rewritten across that span. A vessel that kept a coherent mission for millions of years would be less a spacecraft than an artificial biosphere with its own independent evolutionary history. By arrival, its inhabitants might no longer be human in any sense we would recognize, and the original destination might be a myth embedded in rituals whose practical meaning had been lost. This does not make the idea worthless. It makes it revealing. The generation ship counterargument shows that Andromeda is not absolutely unreachable in the sterile mathematical sense that a finite distance cannot be crossed by motion. It can, but the crossing would destroy the identity of the project that attempted it. If the arrival civilization no longer shares biology, language, institutions, or memory with the launch civilization, then what has arrived? A descendant ecosystem, perhaps. A new species, perhaps. A moving planet that outlived its origin. That may be magnificent in fiction, but it is not the kind of reach people usually imagine when they say humanity may one day go to Andromeda. It is not a voyage. It is a severed branch of life drifting through deep time. The same distinction applies to probes. A robotic probe does not need to preserve a society or a mind. It only needs to function, or at least preserve data long enough to report. But even here, the Andromeda distance is merciless. Electronics degrade. Power systems fail. Interstellar dust accumulates risk. Cosmic rays damage materials. Navigation errors grow. A probe traveling for millions or billions of years must survive longer than mountains, longer than species, perhaps longer than stable surface conditions on Earth. Even if it arrives, transmitting data back requires another 2.5 million years of signal travel. The civilization that launched the probe would not be waiting in any recognizable way. The mission's success would be decoupled from the people who paid its cost, built its instruments, and asked its questions. The probe could become a messenger with no people. Some may answer that descendants are enough. We do many things for descendants. We plant trees under whose shade we will never sit. We preserve knowledge for people unborn. That is true, and it is one of the noblest features of civilization. But it also has a scale. A tree grows in decades. A university can preserve knowledge for centuries. A civilization may carry texts for millennia. Andromeda asks for continuity across millions of years. That continuity has no precedent. It may not be impossible, but it is not the same moral category as building for grandchildren or even for descendants thousands of years away. It is building for beings so remote that they may be as different from us as we are from the first stone tool makers, and then expecting them to care about a question launched before their world, language, or species existed. This is why the distance to Andromeda is not merely an engineering problem. Engineering problems have parameters: mass, thrust, energy, shielding, guidance. Andromeda has all of those, but it adds identity. Who is the traveler after millions of years? Who is the receiver after millions of years? Who owns a mission whose timescale exceeds the durability of cultures, perhaps of species? These are not sentimental questions added after the physics. They are part of what makes the physics meaningful. A journey is not only displacement through space, it is continuity of purpose through time. When the time becomes too large, the journey may continue as motion while ending as intention. The galaxy also forces a correction in how we imagine maps. A map on a screen gives the illusion that all points are available. You can zoom out from Earth, see the Milky Way, see Andromeda, see the local group, and the act of zooming makes the universe feel navigable. The cursor crosses millions of light-years in a fraction of a second. The mind mistakes representational access for physical access. Digital maps are powerful because they erase the cost of scale. Astronomy needs maps, but it also needs a discipline against the lie maps can tell. A dot labeled M31 is not a place in the same sense as a city labeled on Earth. It is a record of light, a gravitational relation, and a distance so large that the line drawn between here and there is not a route but a confession. But there is a similar deception in simulation. Watch a visualization of the Milky Way and Andromeda approaching, and the merger may unfold in 30 seconds. Spiral arms stretch, tidal tails arc outward, stars scatter. The two cores swing past each other and merge into a glowing remnant. The simulation is honest about the dynamics, but dishonest to the nerves, because it compresses billions of years into less than a minute. It makes gravity seem swift. It makes intergalactic distance seem theatrical rather than patient. The real event, if it happens, unfolds so slowly that no biological observer could watch the drama as drama. A night sky might change over thousands, millions, billions of years. The merger is real, but its emotional tempo in a video is a translation, not an experience. This matters because the human brain is vulnerable to compressed time. A map compresses space, a simulation compresses time. Together they make the universe look more accessible than it is. That is not a reason to reject them. It is a reason to use them consciously. The claim here is not that diagrams and simulations are wrong. It is that every representation of Andromeda must lie in at least one dimension. If it shows the galaxy clearly, it hides the distance. If it shows the distance honestly, the galaxy vanishes into a point. If it shows the merger visibly, it hides the duration. If it shows the duration honestly, nothing seems to happen. The true scale cannot be held in one image. It has to be reasoned through. Andromeda therefore becomes a test of scientific maturity. Can we admire the image without believing the image gives us access? Can we watch the merger simulation without forgetting the billions of years? Can we call the galaxy next door while remembering that the door is made of 2.5 million years of light travel? A childish imagination chooses one side. Either it is close and therefore reachable, or it is distant and therefore irrelevant. A more disciplined imagination holds the tension. It is close in the cosmic census and unreachable in human practice. It is relevant to our understanding and irrelevant to our travel plans. It is part of our gravitational future and outside our civilizational horizon. Every one of those statements is true. There is also a quiet, practical consequence for the search for meaning beyond the Milky Way. If we dream of finding other minds, Andromeda shows that even success could arrive in a form that hurts. Suppose a future telescope detected a clear technosignature from Andromeda, something artificial in a spectrum, a repeating signal, an unmistakable sign of intelligence. The discovery would be one of the greatest in history. It would also be a discovery of the past. The civilization responsible might have vanished before Homo sapiens evolved, or it might have transformed beyond recognition, or it might still exist, but there would be no way to know for millions of years. The detection would answer one question and sharpen another. Not are we alone, but can separated minds ever share enough time to matter to each other? That possibility makes Andromeda both more thrilling and more lonely. A living galaxy could be full of stories, but every story is delayed beyond contact. Worlds may orbit 1 trillion suns. Some may have oceans, continents, storms, microbes, forests, machines, ruins, or nothing at all. We cannot know most of it. We can infer populations statistically. We can say planets are common around stars in our own galaxy, and therefore likely common elsewhere. We can model habitability in broad strokes. But the particular lives, if any, are hidden behind distance and time. Andromeda is not empty in imagination. It is overfull. The tragedy is that its possible abundance does not translate into relation. This tension should not be softened into a simple message that humanity is trapped. Trapped is too narrow and too dramatic. We are not trapped in the way a prisoner is trapped. We are situated. We occupy one point in a universe where light lets us know more than we can reach. Our situation includes limits and gifts. The limit is physical access. The gift is evidence. Andromeda's photons do not carry us there, but they carry enough of the galaxy here for understanding to begin. The correct emotional response may not be despair, but chastened wonder. The feeling that comes when something is more beautiful because it is not ours to enter. The ending should return to the first image, because the first image contains the whole argument, a faint smudge in a dark sky. To the eye, it is small. To the telescope, it is a galaxy. To cosmology, it is a member of the local group, a massive spiral, a gravitational partner, a future question. To human ambition, it is a temptation. To physics, it is a distance, about 2.5 million light-years. That distance is not merely a number. It is a filter that removes fantasy from scale. It tells us that the nearest major galaxy is close only when the comparison set is the rest of the universe. If you could watch the sky across billions of years, Andromeda would change. It would grow larger if the galaxies approach as expected in many models. Its shape would distort. Its stars would scatter into our sky. The Milky Way's own structure would warp and respond. Eventually, perhaps, the two islands would become one larger island, and the word Andromeda would refer not to a separate neighbor, but to part of our merged galactic history. No living human will watch that full transformation. No civilization like ours can plan around it as an event. But the knowledge of it changes the night. The smudge is not only distant, it is dynamic. It is falling, perhaps toward us, across time that makes mountains seem temporary. And if the merger does not occur within 10 billion years, if future data refine the motions and show that the galaxies pass in a different way before returning or not returning, the lesson remains. The distance is so great that even the future of the nearest major galaxy cannot be narrated with easy certainty. Prediction across billions of years becomes a probability field. That is the honest posture. The galaxy next door is close enough to affect our gravitational future, and far enough that its fate with us remains a calculation refined by new measurements. Certainty would be comforting. The universe has not promised comfort. One day, perhaps, our descendants will build instruments that make Hubble's great mosaic look primitive. They may resolve fainter stars across Andromeda. They may map planets indirectly through microlensing or other techniques. They may identify stellar streams in exquisite detail. They may use gravitational waves, neutrinos, or other messengers to learn things we cannot. They may reconstruct the galaxy's history with a precision that would make today's astronomy seem like a sketch. But unless the laws we know are bypassed by realities we have not discovered, those descendants will still not walk there in the ordinary sense. Their knowledge may become intimate. Their access may remain null. That possibility should change how we speak about the universe. The cosmos is not merely big. It is divided by light time into regions of possible action, possible communication, possible observation, and pure inference. Andromeda lies in a strange category. It is observable in great detail and gravitationally related to us, but not meaningfully accessible. More distant galaxies fall even farther away along that ladder. Some are observable but unreachable. Some are now beyond causal contact. Some may exist beyond the observable horizon entirely, forever outside any evidence we can collect. The universe is not one category of knowable thing. It is layered by distance into different forms of relation. For a human being beneath the autumn sky, that may sound too abstract. So return to the simpler truth. The light you see from Andromeda tonight began traveling before there were humans to see it. It crossed space while Earth became the world of our ancestors. It arrived at a planet where a species had learned enough to understand that the little cloud was not a cloud. That is a remarkable coincidence of timing, though not a coincidence in the mystical sense. Photons arrive continuously. We became able to interpret them late. The universe had been offering the evidence all along. We had to become the kind of creature that could read it. Maybe that is enough. Not enough for conquest, not enough for travel, but enough for a deeper kind of participation. We participate in Andromeda by being made of the same cosmic processes, by sharing the local group, by exchanging ancient light, by allowing its distance to correct our imagination. We do not need to reduce the galaxy to a destination to let it matter. It can remain what it is, visible, beautiful, knowable, and beyond reach. A boundary does not diminish a thing. Sometimes it gives the thing its shape. The next time you find Andromeda in the sky, do not let the word neighbor fool you too quickly. Let it remain a neighbor, but a cosmic neighbor, a word stretched until it nearly breaks. Let the silver smudge become 1 trillion stars. Let the trillion stars become 2.5 million years of light travel. Let the light travel become the entire rise of the human line. Let the distance become a wall not of stone, but of time. And then hold both truths together. It is the nearest major galaxy. It is also impossibly far. The force of the thought comes from refusing to choose only one. That refusal is the central discipline of astronomy. The moon is close and unreachable without rockets. The sun is familiar and lethal. The stars are points and suns. The Milky Way is home and almost entirely unknown from within. Andromeda is neighbor and abyss. The universe constantly offers paired truths that human intuition wants to separate. A calm mind learns to hold them together, and when it does, the sky becomes less like a ceiling and more like an argument made of light. Andromeda does not ask to be reached. It does not care whether we call it near or far. It burns with its trillion stars because gravity, gas, time, and dark matter made it so. It sends light because stars cannot help shining. It approaches or perhaps dances toward a future encounter because gravity shapes the local group across billions of years. The human meanings are ours: neighbor, destination, boundary, mirror, laboratory, exile. The galaxy simply is, but the meanings matter because they reveal how we understand our place in the architecture of everything. The strongest final claim, then, is not that humanity will never achieve anything beyond Earth. That would be small and probably wrong. The stronger and safer claim is that Andromeda teaches the limit of an old dream. The dream says the universe is a frontier waiting for us. The evidence says the universe is first a record waiting to be read. Some frontiers may be crossed. Some may only be studied. The nearest major galaxy belongs, for all practical and scientific purposes we can now defend, to the second category. It is not a future colony. It is a cosmic document written in stars and delivered by ancient light. And this document has already changed us once. Before Andromeda was measured, the Milky Way could still pretend to be everything. After Andromeda, the universe became a population of galaxies. Perhaps the galaxy has another lesson now, one suited to an age that has grown comfortable with grand technological dreams. It tells us that knowing the scale of the universe does not grant ownership of that scale. It tells us that observation can outrun travel by millions of years. It tells us that the first galaxy beyond our own is already far enough to make the word journey tremble. And it tells us that the universe is generous with light and ruthless with distance. So stand under the dark and let the smudge remain small. Do not force it to become dramatic. Its faintness is part of its power. A galaxy that taught us the universe was larger than our ancestors imagined now teaches that largeness has consequences. It is not only a source of awe, it is a boundary condition for every future we imagine. The nearest major galaxy is visible to the naked eye, and no human mission can reach it in any meaningful era. That is not a contradiction to be resolved. It is the truth that makes the sight so strange. The light has arrived. It has crossed 2.5 million years of emptiness. It has survived the expansion of space, the motion of galaxies, the dust of our own sky, and the weakness of human eyes. It ends its journey in a retina, a camera, a telescope mirror, a detector cooled and waiting in the dark. We receive it, and for a moment the impossible distance becomes knowledge. Not contact, not possession. Knowledge. A small thing, maybe, against the scale of a galaxy. But perhaps not so small. In a universe where most things do not know one another at all, to receive ancient light and understand it is already a rare kind of miracle. Andromeda remains where it has always been from our brief perspective. A silver wound in the autumn dark, the nearest great island beyond our own. It is coming toward us slowly, or perhaps toward a complicated future still being measured. It is filled with stars we will never orbit, planets we will never walk on, histories we will never witness except as delayed light. It is close enough to see and too far to touch. That is the final shape of the argument. The galaxy next door is not a promise of travel. It is the first clear border of the observable prison, and the first great proof that the universe can be intimate to the mind while remaining unreachable to the body. Look at it anyway. Let it be beautiful anyway. Let it correct you anyway. The distance does not make the galaxy less real. It makes reality larger than desire. And if there is comfort here, it is not the comfort of mastery. It is the quieter comfort of truth. That a small, temporary species on a small planet can look across a gulf older than itself, name what it sees, measure how far away it is, and accept that the nearest major galaxy is both our neighbor and an abyss. Visible, ancient, knowable, and for any journey that preserves us as ourselves, forever beyond reach.